Thank you very much for your introduction, Benjamin, and thanks a lot for the invitation with Aziz and you. So yeah, it's a joint work between myself and Jean-Pierre Barbeau. So it's I would say a long story. About a couple of years ago, I started this project. So I will introduce you a bit at the story of the project. So yes, the purpose of this presentation is to present you a connectome-based inference of dynamical neuron wiring using a control approach. And what the talk today is about some very preliminary results. So about the structure, the methodology, the structure, and some basic results to be discussed, and of course perspectives. So to begin with, I will introduce a bit some very basic concept about control theory. So control theory is about controlling a system. So considering, for example, a process or a system to control, using some specific output to be controlled, we take some measure that gives value, using, of course, some sensors. And from the measurement, we compare with what we call generate a reference or desired output. We compared the reference with the measurement, and the controller deduces a control signal that is sent to the actuator, and the actuators in response do control the system. Okay, so basically, yeah, what is written here, the goal is to control outputs of a system to desired values whilst ensuring a desired level of performances. Okay, so basically, asymptotically, I would say the actual output would track the reference trajectory as close as possible. So basically, if you have, for example, a heater, you set the temperature to, for example, let's say 20 degrees Celsius. It is expected for the heater to converge to, let's say, 90, 95 degrees, sometimes 20, the correct value, but it should remain very close of the reference that has been set previously, despite perturbations. And for example, if you open the door, it's very cold outside. The temperature can, of course, decrease, but the heater would increase its power to try maintaining the temperature to 20 degrees. So that's a very basic example, but I would say the fundamental of the closed loop that we are going here to make the learning process of the neural network. So I will go to this direction after. So about the controller, many controllers exist, like the class 6, like PID, proportional, integrative, and derivative controllers that are the very standard in industry. We have also sliding modes. We have robust control. So a lot of structure. And myself, I dedicate my work to what we call model-free control. So it has been developed, so I can now switch, by Professor MICHEL and Professor Cédric Juin, that have been working on this strategy since now about, let's say, 10 years ago or 12 years, since 2008. And this was a very challenging work, especially to design new application during these years. And it works very well. It has been successfully published, a lot of publications. And I've been working on that since my thesis that I defended in 2012. I started during my PhD, and I decided to try working, despite my contract, to try working on that and contribute to applications, to a lot of applications, to maybe theory also. And a couple of years ago, I decided to try to see if it's possible to use model-free control as a learning algorithm. So what I wrote here in the goal, considering a control law as a training or learning algorithm for neural network. So here I do apply the model-free control methodology because, yes, it's my current trend, my current work in control. So it was the opportunity to test this algorithm. So the outline of the presentation is first, to present you what is, roughly speaking, a model-free control methodology. So the principle, what is the core of the model-free control as the author designed initially. My own control law, which is a derivative-free version. I named that paramodel control. It can be used as an online optimizer. And since it can be used as an online optimizer without the use of numerical derivative, it could be possible, a priori, to use the control as a learning algorithm to train neural networks. So first, I will present an amazing way to solve AX equal B. So that was, in fact, the first application I made with model-free control. And then application to a basic neural network. And the biggest part, the most recent part is to apply it to a growing neural network like what we call a connectome for now. And then I will conclude the presentation with open perspectives. So to begin with, let's start with the application of the principle of the model-free control. So initially published in 2008 in a French journal, ESTA journal, and then in 2013 in International Journal of Control. So considering a system, whatever you want, electromechanical, Schroter engine, pump, biology. Also, I made also some epidemiology. What you want, it should be possible. It is assumed to be possible to derive, so from a complex system, to derive a simple local approximation that is called local model or ultra-local model. So this ultra-local model takes the input of the system, the output of the system. An ultra-local model is calculated at each instant. It is derived at each instant. And from this local model, we calculate the model-free control that is based especially on the local model to deduce the control to apply to the system. Okay? So the model-free control is based on the control of the local model. This local model compensates the poorly known parts of the plant as well as the various possible disturbances. So basically, it's kind of, I will show you, it's kind of a very simple approximation, basically a first order approximation, like a first order Taylor expansion. First order Taylor expansion for which at each instant it is updated to calculate. So from the U is the input of the system, the numerical derivative of the system, we calculate what we call the ultra-local model. So Y derivative nu equals alpha U plus F. F is called the ultra-local model. So to summarize, from any complex model, it could be replaced by an ultra local model, for which you have here the definition. So again, it's kind of first order or second order local approximation. Practically, yes, nu can be is considered as equal to 1 or 2, but 1 is sufficient. So basically, we can say that it's a first order ultra-local model. From this local approximation, yeah.
Yeah, we have a question from Aziz.
Yeah.
It's what's your F? How do you compute your F initially? What is
F is computed from the knowledge of U which is the input of the system. So it's known, because it's if I take here the U is the control signal, so it's known because it's the controller. U is known, and Y derivative is the time derivative of the measurement. So if I go a bit back, here U is maybe here U is the variable that controls the system, okay, and Y is the output of the system. So both are known. The problem, I would say, not the challenge, but the issue would be to estimate the time derivative of Y, because it's necessary to recreate a local dynamical model. We need to derive to calculate the time derivative of Y. First order, it's enough. So once we have U, we receive from the sensor, we receive Y, we make the first derivative, and then we deduce F. Basically, yeah, it's just a simple algebra formula. Okay.
Thank you.
So it's a time derivative of Y minus alpha U equals F. Okay. So at each instant, you can imagine that you calculate F as the control is running. You calculate F at the same time, and F is replaced, is induced, is replaced inside what is called model-free control. So here in green, you have the expression of the control law. So U equals 1 over alpha. Alpha is a real parameter, tuning parameter, minus F plus the reference. Okay. Reference also power nu for the derivative. So nu equals 1 or 2, plus a basic corrector of the error. So if I go back about the scheme, that U equals minus 1 over alpha minus F is the model-free control that is in this block. So that's basically the controller. Okay. So that's basically the controller that assumes that the system is modeled by a local approximation F. So that's what we call model-free control, by the fact that F, you see, the F
Loïc,
is...
Loïc.
Yep, oui.
Which means that c'est Aziz.
Oui, Aziz.
Which means that you have... Attends, j'arrête le micro.
Ah, je n'entends plus. Aziz, tu avais une question?
I said that
Yep.
you have some error behind your story here. I can't see the origin of your error. I don't understand. I see clearly that you need a correction.
Yeah.
Because you have an error.
Mm-hmm.
This error comes from what?
Yeah. The error here, in fact, the error is, sorry, here, the error is, sorry, it's It's the tradition in control. Huh? That's why sorry for that. The error is in fact the difference between the desired trajectory and the output. Okay, so the correction basically, if I go back on here, the error is the difference between the desired trajectory, the reference, and the measurement. Okay, so basically, if you are very far at the beginning, for example, if I take a concrete example, if you have a boiler or a heater, you have the heater is okay. You have a fresher room. You have maybe 10 degrees, and you expect 20 degrees. Okay, you have an error of 10 degrees. Okay, so that's only the difference between the reference and the measurement that normally should go to 0. That should converge to 0 while the control is running. And yes, what is called correction here is what I said initially is kind of PID control, so proportional integrator derivative. So that's the very, very standard in control. You can take only, for example, a simple gain. For example, the control signal could be K times the error. So you just amplify the error, okay? And the fact to amplify the error for some very specific, for some simple system, you have convergence of the closed loop, and the output should converge to the reference, even with a basic controller for very basic simple case. Okay, so that's the particularity of the model-free control, is that you use a basic correction, so basic, very classical correction, for which you add the model-free terms. So here, if you can see my mouse, the 1 over alpha minus f plus y star is the reference, okay? And basically, we have the property of the model-free, the expected property of the model-free control, provided that you can see here, the control is based on the ultra-local model and not on the complex model, roughly speaking. You can see that F is injected inside the model-free control law, since it takes into account the local dynamic of the system as described by the ultra-local model. Okay? So practically, it's the same conceptual simplicity as PID controllers. I mean, from the coding part, it's very simple to implement. It's really the same as very basic control from the coding part, and no a couple of lines of codes. We do not need precise modeling or identification of the system, because since we assume that the system is modeled as a first order system. So basically, yes, we do not need any precise modeling, since again, I remind that F is compensating the polynomial parts of the plant as well as the various possible disturbances. So we do trust, I can say that, we do trust finally F to be, I would say, enough representative of the complex system to be, I would say, a realistic approximation of the complex model, upon which the model-free control reacts and can calculate the control U in order to have a good tracking performances. Okay. So the most disadvantageous of this strategy is that it needs the evaluation of the time derivative of possibly, or I would say possibly, but I would say, practical point of view, mandatory noisy signal. If we are doing, if we are controlling a realistic process, of course we do that. We do have noise, and we have to compensate the noise through time derivative. So basically add additional filtering and so on. So we have a lot of techniques, but it's not the problem. But yeah, it's, I would say, the most disadvantageous part. It needs the time derivative. Okay. So here it's some review of model-free-based control algorithm. So the initial version from Professor Fliss and Professor Join in 2008 that has been released as an extended PID controller that uses a very simple local approximation of any complex system. And my own version that I released in 2012, which doesn't contain, so it's a kind of variant, which does not contain derivation, time derivative. Okay, so I will show you that it could be considered as a self-tuning integrator, for which we have we had very interesting application that we released with my team in Nantes recently. So especially the epidemiology control of the HIV that has been published in 2022 with Christiana and Delphine in journal and the journal. And most recently, the CFD computation with the control of the Navier-Stokes equation through the application of the blade section. So using computational tools that has been published in the last ECC conference in 2014, 24, sorry. So you have the papers if you are interested. All are online, of course. So now my version. So it was also my of course my expectation to test my own version of model-free control for the neural network. For a basic reason is since it does not contain derivatives. So I guess that, but it remains to prove for future works and for perspective that I guess that the fact that no derivatives are involved in my control law would help to the learning process to converge. But again, it needs to be proved, to be mathematically proved in future work. So my version is it's a variant. It considers an integrator. So here you can retrieve the y star minus y. So it's the error of the tracking, as we discussed previously. So y star minus y is the error of the tracking. We compute the integration. So it's a basic version of the integration for the presentation. This integrator is multiplied by a psi function, which store information and has a forgiving factor model as an exponential part, a converging exponential part. Okay. So basically, yes, psi is a time series that adjusts online the gain, because you see, psi is multiplying the full integrator. It adjusts online the gain of the integrator, which is so associated to a forgetting factor. Okay. So for the moment, yes, I do not have a formal proof that we are working on with Jean-Pierre. We do not have formal proof that this algorithm works in closed loop, even for basic system. So it's an ongoing work. We are working on. The interesting point of this formulation that I derive from, I would say, trial and attempt, trial and error with the original version. So again, it's not formalized currently. It's an integrator that is adjusted online by a forgetting factor, okay, with an history of the convergence that make also the importance, the property of model-free control. Okay. So an additional, an interesting application is to consider what I call the paramodel control. Is to consider this control law as an online optimizer in closed loop. So, for example, here we start from two convex functions, FA and FB, two very simple and quadratic convex functions that are a bit delayed in X. Here you have the minimum at 30 and here the minimum at 40. We start here at an initial condition and then, okay, we start the control. It converges to 30, okay? It stays at 30 without, there is no reason to move since it has been converged. And at an arbitrary time, we decide to switch to FB. So FA switch to FB. So of course, the minimum is no more than minimum. It switched to this point. And the control is able a priori to react and reconverge to the new local minimum at 40. So what I call here is that we have a priori stabilization of the tracking, first at the FA minimum, then at the FB minimum. So I decided, well, yes, to continue on this way and say, okay, if we are able to make a kind of online optimizer, of course, it's a very basic version. It's not at all. I do not claim, of course, that I am very up to date regarding derivative-free optimization. No. It's a very basic version highlighting some property of paramodel control. That's it. Okay, for this version. I consider to go towards. I have some question in the chat, but if I don't know if I answered all of them, or maybe at the end of the talk would be easier. Of course, you can interrupt me if you have question. Before considering neural network, since neural network is kind of multiple agent system, I started to deal with the basic solving of linear system AX equal B to solved in closed loop. So here you can see again the closed loop. You have the system. Of course, it's not a dynamical system, it's a static system. Y equal AX, for which we close the loop with the paramodel control, and the paramodel control, the controller, drives directly x1, x2, and x3 to make finally y, the output y, as close as possible to B, to y star, so the reference equal B. Okay. So again, in closed loop, we do impose B, that's the output vector. We do impose B, and we do expect from the closed loop that Y converges to B. Okay, so the error here should be equals to 0 or very close. And x1, x2, x3 finally do solve the system X equal B. Okay. So to running computation, and you can see that it works pretty well, because here it's over a pretty long time. On the left, you have so the reference in red y1, y2, and y3, and you see that it converges to the y output converges to the vector B. So similarly, here from the X vector, it converges to the true solution that I noted here, X star. After some transient here, it converges to the true solution of the system. So basically, I assume that it works at least for a basic system. So again, there is no proof of convergence of this application we are working on. Next application. So the neural network that I made just after the matrix system. That was my first attempt, as I said, that I tried to yes, I was accepted to the APMS in 2021. I released this on archive in 2019. Okay, and the fact is, but I will give some info about that later. It's amazing because when I was working on that at this time in 2019, the MIT released a paper about using adaptive control law and relative control algorithm to machine learning. Okay, so yeah. It's amazing that, yes, while I was working on that, yeah, the MIT released the paper, so it gave me more motivation to release the first application on that at this time. So considering a three neurons network, we have two inputs and one output. We have 6 synaptic weights. The goal is to train, considering a data training set, X1 train, X2 train, and Y train. The goal is to train the neural network in such manner that the goal is to adjust the set of the weight, WI, to fit with the data training using the proposed algorithm, such that, in fact, we are training in closed loop all synaptic weight, in such manner that the neural network can track finally the training data on Y. Okay. So the control scheme, again, the same, of course, the same architecture. We consider the neural network as the system to control, for which Y is the output. Y train, so the data training from the output is the reference, tracking reference of the system. Okay. And you see that the goal is to make, after convergence, to make Y equals or very close to the data training of Y. Okay. So of course, considering a fixed input data training, input 1, input 2, we fix also Y. Okay. And we run the system to learn to make the output, the synaptic weight learning, in order to match Y with the reference on Y. Okay. So that was my contribution with the model-free control, and that has been proposed also by the MIT at this time. It allows a priori online update of the network with respect to topological network modification and training data changes. That's, I believe, an interesting property of using kind of model-free control online to make the learning process of the neural network. For example, here you have in the left, you have the dynamic evolution of the weight. So there is only six weights. You see that all are converging. I applied some disturbances here, and it continues to converge. Okay, so I will go in detail a bit just after. Here on the right, you have the red curve converging towards the training data on the output. We make a perturbation, and again, it continues to converge towards the reference. Okay, so to be a bit to go into more details about these figures, we start from an initial data training set. We need to start with something, and so of course we start with something. We decide to force. Finally, we cut a connection. We force W4 to 0. We cut the connection. And also, we change the data training set. So you see that here, despite the perturbation with, in black, the problem with the cutting the connection, it changes the topology of the network. And so it induces reconvergence. The control reacts to make reconvergence of the system. Okay, so here it's on the synaptic weight perspective. Here on the output, it's the same. It's the image of the synaptic weight. We start from the initial training that wanted to converge. If we did not make any perturbation, and you can see the red that it should be able to converge without any problem. We force Y4 to 0, so we cut the connection. It continues to tracks and finally reconverge. Well, I don't know if reconverge is really English, but yeah, you understand. It reconverges to the reference. So as a conclusion from this simple case, I do assume that we have a priori restabilization of the weight according to the different changes of the data training and the network topology, which, from my opinion, is very, very interesting because it would allow to render the network dynamically optimizing learning according to data, according to whatever on the network. Especially moving connections. We decide finally that, for example, that some connections are not useful, close to 0 for the way. Okay, we can remove them. How do they impact the other connection? How do they influence the other connection? Well, using this example, it should be interesting to investigate in the future. Okay. So the most recent perspective concern, yes, what we have called with Jean-Pierre a connectome, which is not completely for the moment a connectome because we still have a lot of work to do for that. But nevertheless, yes, I do present the methodology and that is currently released and current future perspective for the connectome parts. So we do propose here a growing neural network. Of course, as an extension of the previous work. Considering, for example, let's say two, for example, 2 or 3 or n inputs in yellow. So I1, I2 are, for example, 2 basics input. And of course, we can increase the number of inputs as we want. Same for the output. We have output 1, output 2. So 2 outputs. Of course, we increase to output n. And we have inside kind of neural network, very messy, I would say. So there is no, I say messy because there is no symmetry. We do not have a priori any symmetry. It can be like in the brain, finally, completely, I would say, random distribution of the neurons. Considering all connections, all moving connections between inputs, the neuron, and the outputs. Okay. So the principle is the same as I presented previously. How to learn, how to make the learning process. So first, we consider a learning based on the closed loop algorithm that make finally every weight, synaptic weight learning according to the information that are given on the output as well as the input. Okay. So the closed loop is tracked. We use a reference given by the output, and the information from the input propagates through the neurons, considering the closed loop that learns in real time to fit every synaptic weight with the kind of optimal combination in order to make the full network learning. So in addition to that, here I represent in blue closed loop based learning, so descending array, because from the data that are given as a training data on the output, we go down to learn every synaptic weight. And at the same time, we do consider also to propagate statistic from the synaptic connection. So I mean that every neuron is connecting to his neighborhood, and we do expect that every synaptic weight can give a statistics about the current configuration of the synaptic weight that could give in the future, and that could give additional information to improve the learning process, and especially to take decision. Okay. So what we do expect finally with this growing network is first, of course, to learn. That's the standard property of neural network. Learning with closed loop, provided that we have we can cut connection. We can reconfigure. We can reconfigure the whole connection online in real time, and take benefit of such reconfiguration to dispatch information in a maybe more precise way, or introducing some granularity inside neurons. And in addition to that, we do emphasize the fact that we would like also to propagate statistics of synaptic weight while we are learning. Okay. So that's basically, yes, that I would say the at least two contribution we would like to reach as perspectives. Here below you have the references, what I said, and the CDC conference is the paper of the MIT, G. Godio, the paper of the MIT, and below you have Sophie Cerf and Eric Rutten from INRIA in Grenoble that also presented some trends with neural networks, and in particular with the learning process. Okay. Learning process that could be done especially with closed loop. So I guess we would have some very interesting challenge with that in the future. So yes, the project is available on this link on my website. So the first attempt I made is to at least make some convergence of 6 neurons. So it's not a big deal, of course, for the moment, because I'm trying to first configure properly the code and to make the propagation efficient. So first, yes, 2 inputs and 1 output, so 6 neurons to learn. For example, we do learn a time derivative of a sine function, which is very easy to calculate. So basically, input is the sine function, output is the time derivative, and the point is to make the neuron learning what is the derivative of the sine function. So here I do represent graphically the convergence of the synaptic weight. So that's the 6246. The six first synaptic weights, so basically the three first neurons that are converging pretty slowly, but apparently it's converging. And we have also convergence of the final, I would say final, but the last, the output neuron number 10. You see that its synaptic weight are converging toward a certain value, as well as you see that the control tries to minimize. You see here it's very highly dynamic, very disturbed, and it seems to converge pretty slowly to some value. So hopefully that, but it needs to be verified. Hopefully, the neuron network has learned something. So for the moment, it does not mean checked. For the moment, we still we are working on that, but at least we have some convergence. So a priori, stabilization of the weights through the training phase. Okay, and the statistics. So what I said before, typically we take the average. Take the average of all synaptic weight at each instant. So the mean value, the average of all synaptic weight at each instant, and the standard value, so the variance in French, standard value, and both are also converging. Okay. So of course, it's, as I said, proof of concept. We need to, of course, develop this framework to see how to combine, especially the statistics with the internal learning. Okay, so that's kind of challenge to see how we could take decision. We could take decision from this additional information, additional statistical information from the wiring. Okay. So before concluding with the perspectives, I would like just to go back on this scheme to just simply emphasize the fact that the next trend, even if it's not for the moment, it's coded, but it's not in operation. It's to create kind of granularity for each neuron in the sense that the wiring are evaluating dynamics. I will show you the video just after the presentation. The all synaptic weights, all connections are dynamically evolving in real time. And what could be, I guess, very, very interesting is to see, okay, for example, taking these neurons, we have first information from this path, and maybe we could have other information given by this path or this path in separate dimension, I would say. So to take benefit of connectome perspective is to see, okay, we have kind of dynamic of cables, of connections. So it could be very interesting to take benefit from this from the configurations of the connection of all connection to mix information in maybe some granularity dimension, and in addition to take also into account statistics. So that's why we call that kind of connectome perspective, because we would like to make everything dynamic and see if it's possible to create correlation between the connections and the informations. Okay. So basically, yes, I have said most of that during my talk as open perspectives. So of course, it's a very prospective work to be generalized toward large scale neural network, including, of course, cluster analysis of the neural-based information. So you can imagine that if we have several outputs, of course, it would be essential to make cluster and dispatch control law according to outputs, because a controller can take only one input. So after we have to clusterize, to partition, to make a partition of the network and create cluster for which the closed loop will take appropriate information in order to make the learning process. Since, as I said, and since it's very like in the brain, very spatially, how to say, messy, I would say messy distribution of neurons, a kind of random. It would be interesting, of course, to create some probabilistic based, calculate some probabilistic based interaction, and in particular Bayesian inference, to help the learning to create or disconnect connections. What I introduced the in-neuron granularity via connection dynamic. So introducing, for example, multiple dimension for every neuron to store information, taking into account the connection of the active connection connecting to every neurons. Of course, we can change the model, because here I use the basic ReLU model, so we can use spiking neurons. Emphasize statistic propagation. So what I explained before, so try to build a framework to help decision making, and in the future and long perspective, robustness to large set of training data. So yes, it's a work in progress. Here you have the references that have been that help for the work, and I show you the video to conclude my presentation. So before starting, here you have two input neurons in yellow, two blue internal neurons, and here, so it's in the left, in the right, you have the trajectory of the synaptic weights that will be running while the control is running. So let's start the video. So here you see that, yeah, the connections are random. We create neurons, and at the same time, you can see the synaptic weight evolving. So it's accelerated. Synaptic weight evolving towards the expected references. So here you can see that, yes, we create a new neuron. So it influences all previous neurons. So it's restart the convergence to new references. And yeah, that's it. So yeah, thank you for your attention. That's the end of my presentation. So thank you. If you have questions, I will be very happy to hope to have it been clear. So do not hesitate. Thank you.